In this podcast, we will do a full example of graphing a sine wave that includes scale changes and translations to the parent function from beginning to end. And our example will be y equals 4 sine of quantity 3x plus pi plus 1. And the first thing we'll want to do is do some algebraic rearrangement so that we can see the changes to y as being associated with y, and then we'll look at the changes with x. So we can subtract 1 from both sides, giving us y minus 1 equal to 4 sine 3x plus pi. And we can then divide by 4, leaving us y minus 1 over 4 on the left, and on the right the sine of 3x plus pi. Now that we've got the changes to the variables separated so it's clear what's with x and what's with y, we can go ahead and reverse everything as the graph standardization theorem suggests that we do. So the x variable in the equation is multiplied by 3 and then pi is added. And so to fully reverse that process, we would first subtract pi, and then we would divide by 3. And looking at y, it's y minus 1 all over 4 in the equation. The last thing that was done was the division by 4, so the first thing we'll undo is the division by 4, and we'll undo the subtraction of 1 by adding 1. Now there's a subtlety in this example that makes it a little tricky, and that is that in all of our work with our graphing of sine and cosine waves, we have worked under the assumption that the scale change is the transformation that comes first, and then that's followed by the translation. And if we want to continue along those lines, we have to rewrite this change to x as x over 3 minus pi over 3. And first of all, note that it's equivalent, right? Algebraically, x minus pi all over 3 is the same as x over 3 minus pi over 3. But what's important is we now have the division occurring before the subtraction rather than vice versa. And this puts us in a position where we can now say what the period, amplitude, phase shift, and vertical shift are. So the period is going to be 2 pi times whatever the scale change was to x, which was 1/3. So we have 2 pi times 1/3, which is 2 pi over 3. The amplitude is the same as the scale change to y. The phase shift is the same as the scale change to x, and the vertical shift is 1. So now we need some scales on our axes. And if we go up to about 5, we should be good. So the vertical shift being 1, we'll sort of locate that horizontally, and then because the amplitude is 4, we'll go up 4 from 1 to 5, and down 4 from 1 to -3, and that will set us up vertically, and now we just need to lay things out horizontally. So I'm going to go a couple of tick marks, I guess, per quarter period, so something like this. And then the period being 2 pi over 3, I'll just declare the fourth tick mark to be 2 pi over 3. Half of that would be pi over 3. Half of that would be pi over 6. And so our tick marks, as we now know, are worth pi over 6. 3 times pi over 6 is 3 pi over 6, or pi over 2. And we can label as many of the others as we want once we sort of have the important points taken care of. Now, this being a sine, if there were not a phase shift, it would start vertically at the middle, which in this case is at y equals 1. And then every quarter period it would do the top, middle, bottom, middle routine, and similarly going back in the other direction. So if it were not phase shifted, this graph would look something like this, and so I'll dot that in kind of as a guide. But it is phase shifted. It's shifted pi over 3 to the left, and fortunately for us, that's exactly half a period, and so it's a pretty easy matter to just take key points on the graph and shift them half a period over, and I'll go through that process with several of these points, and sort of once you get the pattern established, you can just continue it. So our graph will go like so. It'll appear to be a mirror image because of this half period shift. It will appear to be a mirror image of this dotted graph across the horizontal line y equals 1. And there is our graph.